some research that we've done to try and illustrate some of the points that I'm making. And then, of course, there will be a summary. And as I said to Luis earlier, you're more than welcome to get a copy of this talk. You know, and Luis already has a copy, but if he wants a more updated copy, I'll send it to him. And you can make a PDF of the talk. So start off. I always like to start with this talk because as biomechanists, we think of mechanics all the time. And one of the things that we have to really consider is that, you know, how we control the movement as well. And that seems to be left out of a lot of biomechanics talks. And unfortunately, I'm going to leave out motor control from this talk. So, but you can't really separate biomechanics and motor control. That's just my point for today. Now, in loading the human body, and because most of my research is on locomotion, I'm going to be speaking specifically about locomotion. And the major load on the human body during running is the vertical component of the ground reaction force. Now, it's by far the largest. I know we have a fore-aft and a medial-lateral component of the ground reaction force, but the majority of the load on the human body is the vertical ground reaction force. And you can see here, as the person's foot hits the ground, this vertical reaction force is transmitted through the leg. Now, based on the vertical ground reaction force, and this was a dichotomy that was made, I think Ben Onig popularized these two terms in the late 1980s. And since there were two peaks, he referred to one, this first peak here, as a passive peak. And the passive peak, a lot of people talk about this as being an impact peak. And then the second peak is referred to as an active peak. Now, these have definite meanings, and they have influence in terms of we're talking about muscle loading. So this is vertical ground reaction force actually as of a heel toe runner. Even though with forefoot runners or barefoot runners, whichever, you don't see this passive peak obviously, but it is there. I just want to point that out. So let's talk about first the passive peak. And the passive peak is a result of the foot's collision on the ground. And it's generally associated or not associated with muscular contractions. Okay. What it is associated with is shock attenuation, and it's associated with the heel fat pad, which is several millimeters thick, joint cartilage, and lower extremity geometry. In several papers, Martin Buber has, and I will talk about what he shows later, this peak is generally determined, and it's not under muscular control. So how the geometry of the leg is formulated before touchdown actually constitutes this peak. Now, the active peak, this second peak here, it results from an active force applied by the lower extremity onto the ground during push-off. So this is the peak that actually propels you off the ground. And it's almost entirely associated with muscular actions. That's why it's called an active peak, active muscle contractions. Now, this is Martin Bobert's paper in the Journal of Biomechanics. And what Bobert did was he used a kinematic analysis to reproduce the ground reaction force. And what he did was he calculated from the kinematics, he calculated the center of mass of each one of the segments, okay? And the center of mass of each one of the segments, if you multiply it by the mass of the segment and subtract the gravity term, sum all of this up, sum all of those forces of each one of the segments up, and you'll get the vertical ground reaction force, okay? Now, what this means, I equals 1 to n is the number of segments. And so he had 2 feet, 2 legs, 2 thighs, a pelvis, a trunk, 2 upper arms, 2 lower arms, and a head. All of those segments were added together. And what it did would produce really interesting results, because it truly determined what the impact peak was, or sorry, what the passive peak was, and what the active peak was. So what you notice here is this actually is the passive peak, and it is constituted by the support leg. The rest of the body minus the support leg constitutes this peak here, and he referred to it as the body peak, or the body force. Now, if you add these two together, you will get the vertical ground reaction force. And so this gave us an indication of what the, what these two passive and active peaks represented. Now, we did the same thing. This is one of a class project that we did, and we took the ground reaction force, vertical ground reaction force, and decomposed it into an active, the active force, the peak, which you see here, actually coincides at this point with the total vertical ground reaction force, and the passive peak. And you add these two together and you get the vertical ground reaction force. What this is indicating really is what we call the impact peak is really not the impact peak. This is the impact peak here. But because you add these two together, you get this. So in this cartoon, you have the passive peak here, which represents the contacting lower extremity, as Martin Bobert showed us. And the active peak is really consists of this large section here, which was really the rest of the body. And of course, if you add these two together, you get the vertical ground reaction force component. And again, as I said, this passive peak here and the passive peak here, we call them the same thing, but really they're not of the same magnitude. Now, if we look at the components of the vertical ground reaction force, in the frequency domain, the passive peak, we call it a high frequency because it's about 10 to 20 hertz. The active peak is really below about 9 hertz, and 8 to 1 hertz really constitutes this active peak. And this is how we decomposed the ground reaction force in the frequency domain. Now, this peak here, or the passive peak here, if this starts getting up to around 17, 18, 19 hertz, with repeated insults of or foot strikes, that can indicate that you might have bone degradation. So that's why it's very important to notice where this peak is in the frequency domain. Now, the key thing about all of this is that for each foot contact on the ground, the contact load, that is the vertical ground reaction force component, is transmitted through the skeletal system, and it affects all segments of the body. But what happens is The vertical ground reaction force, as it goes up the body, is slowly attenuated, and it gets all the way up to your head. I don't know if any of you have had the misfortune of, walking and you're not looking where you're walking, and you step off a sidewalk and your foot hits and you find your teeth chatter a little bit. That's actually this ground reaction force going all the way up through your body. The good thing is that this is attenuated. It's attenuated by a number of things: geometry, muscle, cartilage, ligaments, bone. All of this attenuates this load. So this was a study that I did a number of years ago, and it was used accelerometry, and we had an accelerometer mounted on the distal anteromedial tibia, and then we had one mounted on the head. And the people were running at a constant velocity, so we know that stride length times stride frequency equals velocity. And what we did in this particular study was we kept velocity constant and we increased the stride length. In other words, decreased, it's the same thing as we can decrease the stride frequency. And what this has an effect of doing is it keeps the person running at the same speed, but it increases the impact force. So what we did first, and this is a picture of the profiles, the leg profile and the head profile. I want you to note, though, that these two are on different scales, okay? And this constitutes one stride. So this is a right foot contact and a right foot contact. Now notice there are two motions of the head here, accelerations of the head. And that's because you only have one head, but you have two legs. And so this constitutes one stride, okay? Now, what we first did with this is that we looked in the frequency domain, and we looked at the particular 10 to 20 hertz region. And you notice this is a power spectral density here. If you can think of these as amplitudes, the amplitudes in the 10 to 20 hertz range are very, very large. If we go to the head acceleration now, the same amplitudes are now significantly reduced. Okay, now this is only one example of one condition, one stride length condition, but all of the stride length conditions were basically the same. So you have active components in your body that will, and muscle being the most important one, that will reduce this or attenuate this force. Now, what we did when we combined all of the data together, so this is stride frequency. So these are the long stride lengths here. And these are the short stride lengths here. Okay. And you can see the relationship here. If this is in terms of frequency, we can look at it in terms of stride length. What we found is the long stride lengths, there was a very, very high impact, as we saw in the accelerometer. And in the accelerometer, this impact was upwards of, I think it was probably around 8 Gs, 8 times the acceleration due to gravity. And the low impact, you can see here, it's, this is down around 4 Gs, significantly less because it's a lower impact. That was the interest. That wasn't necessarily the interesting thing. The interesting thing is no matter what we did in terms of the impact, the acceleration at the head was always around 1 G. In other words, your body does this, and even though the force is large at the tibia, by the time it gets to the head, it's really 1 G. That's basically atmospheric pressure. what you would find in atmospheric pressure. Now, you're probably wondering why, and we did too, because really, when we were doing this, we were kind of naive and we did not expect this to happen. And what we did was we made a statement, and it was speculation, an interesting speculation, that the reason why the head had to be at 1G was to maintain a constant visual field when you were running. You know, you don't want your head bobbing up and down, because you have to see where you're going. And, you know, on a track or a road, this is not as important, but let's say you're doing trail running, it becomes very important. And subsequently, we did several experiments later, which I'm not going to go over today, you know, which showed, you know, how when you present visual challenges, these results change as a result of the visual challenge. I think this was the talk that I gave in Manaus at the Brazilian Society of Biomechanics meeting there a couple of years ago. So, so far we've only really looked at a gross value of loading, and we've inferred that muscles are very important in loading. But so far we've only really looked at a general level of loading during running. And what if we wanted to look at the effect of loading on muscles? Is there a way that we could do this? Well, yeah, there's a couple of ways. And in order to get to the individual muscles, we have to go through a process of calculations. And we have to use other techniques to get to this process of where we can look at individual muscles. And so there are two methods that we commonly used and that we've used in our lab, is to calculate joint moments and the joint resultant forces. And we use a procedure called inverse dynamics. Now, within inverse dynamics, there's two methods that we have used a lot. If you look in most biomechanics, will use what we call a Newton-Euler approach. It's a combination of Newton's equations and Euler's equations. There's another method that's less used, and it's called the Lagrangian approach. Okay, and this is an approach based on energy. And I'll briefly go over it. The nice thing is when you calculate joint moments using either one of these approaches, you get exactly the same result, which is important. So in inverse dynamics, you have a workflow, and you start off, and the reason why it's called inverse dynamics is because you're not directly calculating the forces. You're indirectly calculating the forces. So you start off with the ground reaction forces and the positions of the segments of interest. So what you would do with these is put them into a kinematic analysis. And what you would get out here is the angles, for example. And then what we do is we differentiate the angles and positions, and we get the accelerations here of the angular accelerations and the usually center of mass accelerations. And then we have a couple of equations. The sum of the forces equals the mass times acceleration. You know that is, you know, Newton's second law. And then the analog of that is, the angular analog is the sum of the moments equals the moment of inertia times the angular acceleration. And then there's a process that you take these equations and solve them, and you get the resultant forces, joint forces, and the resultant moments. Now, I'm going to say this now, but I'm going to emphasize it later even more. The resultant moments are not necessarily associated with the muscles themselves. nor are the resultant forces here, joint forces, are they equal to the contact forces in the joint. That's important to know. So in the Newton-Euler method, we would start off, and this is a very general free body diagram. And, you know, some of these, what you do basically is you know what's going on here at the distal end of the joint, and you solve for the resultant forces at the proximal end and the moment at the proximal end. Now I'm showing this in 2D, mainly because it gets really messy when you show it in 3D. And you'll see why in a few minutes. But so these RxD and RYD are the distal forces, including the ground reaction forces. And this is the distal moment, and we'll use these to calculate the proximal reaction forces moment. And what I do mostly is calculate the moments about the center of mass of the joint. You can calculate the center of mass, or you can calculate the moments about the proximal joint or the distal joint. It doesn't really matter. Okay. And so because of this, you'll have three equations. Okay. The sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the moments, which will be I alpha. That's alpha, the angular acceleration of the segment about the center of mass, and the moment of inertia of the segment about the center of mass. Okay, and so we can solve for these values. Okay, so let's go through this, and you know, I tried to simplify these graphs or these free body diagrams as much as possible. But we have a free body diagram for the foot, okay? And we solve at the distal end using the ground reaction forces and I alpha. And there's a moment about the distal end of where the contact of the foot is. And we solve and we find the moment at the ankle and the reaction forces at the ankle. We take those reaction forces and now apply them to the distal end of the tibia, solve, and we get the reaction forces in the moment at the knee. We take these and we apply them at the distal end of the thigh, of the femur, and solve for the reaction forces and the moment at the hip. So it's done usually as a distal to proximal sequence. Now, you know, it sounds very complicated, but it's really not all that difficult. But if you just start off looking at the ankle here, you know, we have the ground reaction forces, and the ground reaction, this is the reaction force to calculate the reaction forces at the ankle. That's this one. Oh, sorry, I've got these backwards. This one here should be up here, and that one should be down there. But this is the ground reaction force in the x direction, and this is something that we often do. Is you know, I've got the y here. This should be an x. You know, the vertical ground reaction for component we usually think of as z, but when we transform it into a 2D, it's usually x and y. So this is the sum of the forces in the x direction, the sum of the forces in the y direction, and mass is the mass of the foot. And then we calculate the moments. And this is the moment, these are the moments about the center of mass. So this is I alpha. This usually is very, very, very small. So it does, you know, it doesn't contribute very much. And this is a cross product, cross product, cross product, and cross product. okay? So these are the moments due to the ground reaction force in the x direction, ground reaction force in the y direction, the reaction force at the proximal end, and the reaction force in the x direction at the proximal end. So the things, these on the right-hand side of the equation, these are all the things that we know. And what we solve for is all of the things on the left-hand side of the equation. So now if we move on to the thigh, or sorry, the leg rather, all of the things on the right-hand side we know, and we solve for all of the things on the left-hand side. All of the things on the left-hand side are the things at the knee. And as you see here, we don't have a ground reaction force anymore, but we do have a reaction force in the x and y directions. And we do the same thing. All of these we know, and we solve for all of these. Okay, that is the Newton-Euler method. And you know, it's a very traditional, tried and true method. I think Elfman actually in 1937 or 38 actually did an analysis like this. A couple of things to remember. Okay, and this came about a number of years ago, and the person that I always blame for this is a very famous biomechanist called Tom Andriacchi, who you may have read papers. And he started talking about internal and external moments. And in fact, internal and external moments are just the same moment, okay, but they're multiplied by -1. So when you use a Newton-Euler method, like I just showed you, you're calculating internal moments. And internal moments represent the muscle and ligament action that move the segment. Okay. The external moment is what we call a loading moment. And they're equal in magnitude, but opposite in sign. That's the problem. I remember one of Luis's former students, Sandra Aliberti. She sat in on my class and I was explaining this to her. And she said, but that's the opposite of the way I learned it. And I said, yeah, but she was, Sandra was a physical therapist. And physical therapists always talk about external moments. And being a biomechanist, I always talk about internal moments. So we finally realized that we were talking about the same thing, but just internal versus external moments. And if you look, this is an example of the moment at the hip, for example. And if I have the moment here, the moment at the hip, and these are all of the components of the moment at the hip. I've just moved them over to this side. So the moment at the hip equals all of this. This would be the internal moment, and this would be the external moment. Why this is really confusing, let me give you an example. In walking, when you first contact the ground, when you calculate the moment for the first, 15, 20% of the foot on the ground, and the internal moment you calculate, okay, is the internal moment is an extensor moment. Now, the reason why it's an extensor moment is that the muscles are acting eccentrically to really slow down the center of gravity. However, if you looked at that as a loading moment, that moment would be a flexor moment. Okay, so you see that you could get a different interpretation, internal versus external moment. Now, it gets even worse when you look at different papers and how these are reported. If you look at the way the muscle, let's look at the calculation. This is the calculation. You notice that flexion is positive, extension here at the knee is positive, and dorsiflexion at the ankle is positive. Okay. The way these are normally reported is all of the extensor moments are normally reported as positive, and all of the flexor moments are reported as negative. You have to be very, very careful when you read papers and see how they're reporting their moments of force. Okay. In fact, I've had many people say, oh, the moments are wrong in this paper. Well, because I always present calculated moments, but many people report moments like this. In fact, the person who popularized this reporting all of the extensor moments as positive was David Winter. And he added up these moments, the extensor moments, to get what he called a support moment. Okay. If he did that here, the support moment would not look anything like it does here. So that's just a note. Now, how do you use this? And this was a paper done by Tim Derrick. And he was looking at energy absorption of impacts running at various stride lengths. And this actually was a follow-up paper to the one that I showed you a little bit earlier. And what we were looking at was how much does the individual joints attenuate this force, the ground reaction force. And basically, if you look here at the large, these are stride lengths now, not stride frequency. So this is the longest stride length. The ankle and the knee provide a lot of the attenuation. As the stride lengths get smaller, and this is what your preferred stride length, the knee still does a lot and the ankle still does a lot. But when you get to even smaller stride lengths, the knee is dominant here and here. And in fact, what you see here is that just about all the way through, the knee is the dominant joint at which the load is attenuated the most. Okay. And of course, the knee is controlled by the muscles that surround the knee, particularly the quadriceps. Okay. And if any of you are run distances at all, and especially run downhill, one of the things you note is you have a high force by, you're falling onto the ground. So what happens is that you get a great deal of muscle soreness in the quadriceps muscles, because those are the primary extensor moments, but they also act eccentrically to control the knee during running. So I wanted to do this just, if you looked at the book, the Research Methods in Biomechanics, this is all in there. But three-dimensional, and I have to admit, I did this in a paper that I published, and it's absolutely wrong. Multiplanar views of 2D force and moments are not a 3D analysis. In other words, you can't take moments in the frontal plane, moments in the sagittal plane, and moments in the transverse plane and say that that is a 3D analysis. It's not. Okay, but all of the assumptions of a 2D analysis, and again, this is a Newton-Euler analysis. All the assumptions of a 2D analysis, they're the same in 3D, with just a few exceptions. In 2D, you have 3 degrees of motion, or 3 degrees of freedom. Okay. That is, you have one along the vertical axis, one along the sagittal or the AP axis, and you have a rotation. It's actually about the axis that comes out of the board. But those are the three equations. But in 3D, we have 6 degrees of freedom now. Okay. We have motions about along all 3 axes and moments about each one of the axes. That totals 6 equations. And here are the equations. The sum of the forces in the x direction, some of the forces in the y, some of the forces in the z. Moments about the x-axis, moments about the y-axis, and moments about the z-axis. Okay. The procedure for calculation is exactly the same. That is, you start with the most distal joints and work toward the more proximal joints. The procedure is the same in that you know what's happening at the distal end of the segment. You calculate what's going on at the proximal end of the segment. Take those, apply them to the next segment, to the distal end of the next segment, and so on, up the chain. So I wanted to show that I don't want to derive these at all, but I just wanted to show you the 3-dimensional equations, ankle equations. When you see a little arrow over something, that's a vector. Okay. So the sum of the forces at the ankle, okay, mass of the ankle, acceleration at the center of mass, and gravity. And it seems strange to think of gravity as a vector, but we have to associate gravity in x, y, and z direction. And then the ground reaction force vector, again, in the x, y, z direction. So here we have the sum of the moments at the ankle. So the moments at the foot, okay, around the center of mass of the foot, the moments of the ground reaction force, and then you have the reaction force, and it's the moment caused by the ground reaction force and the moment caused by the foot ground reaction, or the foot times mass times acceleration. So that's the easy one. What happens when you go to the knee? Now this should look very familiar to you. The reaction forces at the knee, mass times acceleration, and this is the ankle moment. Okay, and of course you will have x, y, z here. What you do is, with this equation here, this part is the moment of the leg itself, the moment of the foot, and then these are the reaction forces that you get. And what you do, and I said and so on, mainly because I didn't have room on this slide to show you the third, you just keep adding terms to this. It seems rather complicated. The only thing that you have to make sure of in 3D is how you present the moments. Okay. You can present them like you could present the ankle moment in the foot coordinate system, or you could present it in the leg coordinate system, or you could present it in the thigh coordinate system for that matter. But you calculate it in the global coordinate system, as we've done here, and then just transfer it to any coordinate system you want. The general rule of thumb is you calculate the moment and present it in the next most proximal moment. So the ankle moment is usually presented in the leg coordinate system. The moment at the knee is presented in the thigh coordinate system, and the thigh in the pelvis coordinate system. But you don't have to do that. So this was a study that Gillian Weir, who was my postdoc at the time, and we did as a group. And what we were looking at is prolonged running and how footwear would affect prolonged running. And here we have hip flexion extension, knee flexion extension, plantar flexion, dorsiflexion. And then this is ABA deduction and inversion, eversion. These are in the frontal plane. And then internal external rotation. And this is in the transverse plane. Many of you are probably familiar with these. Okay. These are in the sagittal plane. But these are a lot less obvious. Okay, and these are all scaled to Newton meters per kilogram per meter, per kilogram meter. Okay, but that's how you would use it. And basically what you can look at, and this is what, Irene Davis has popularized this, is that if you notice the ABA deduction and internal external rotation moments always show differences. And this is mainly because there's a little bit more variability in these, in the movements of these joints, whereas in the sagittal plane, the angles are really large, and basically there's not as much much variability. Okay, now Lagrangian equation. And again, I just wanted to show you that there's more than one way that you can do all of these calculations. And Lagrangian, the equations are derived from Lagrangian's equations of motion. And unlike the Newton-Euler method, the Lagrangian method is a method based on energy. Okay, and the reason why it's a nice method to use is because it looks at the system. Okay, in the Newton-Euler, it looked at the ankle, then the knee, then the hip. But the Lagrange method looks at the ankle, knee, and hip basically all at the same time. And that's what makes it very appealing. So the basic equation here, and these are the derivatives of kinetic energy as a function of velocity. And this is kinetic energy as a function of displacement, and this is potential energy as a function of displacement, and all of these equal to force. So essentially what we look here is the kinetic energy equals mass times acceleration, or the derivative of the kinetic energy is mass times acceleration. And this is equal to the mass times gravity, or the force due to gravity. And this is an interaction term. And the angular case is basically the same thing. It's just you're substituting angular velocity and the two angles equal the moment. Okay. Now, you don't get intimidated by this, but this is the equation to calculate the moment at the hip, moment at the knee, moment at the ankle. And if you look here, let's look at the moment at the knee. If you look here, you've got this is a moment due to the motion of the motion of the tibia and the angular acceleration of the tibia. This is the motion of the leg, and this is the motion of the ankle. Okay, and then you add in the knee, the ground reaction force, and in the X and Y directions. So it's really very easy to do this. This is in 2D. If I did this in 3D, it would probably take more than one slide just to do the hip. And if you look at the book that Luis said that he was going to lecture from, the research methods in biomechanics, these equations are all outlined there. This is very easy to program. It's very, very easy. We presented this in Journal of Biomechanics, and Sandy Whittlesey was a former graduate student. And basically what we compared was the moment calculations, Newton-Euler versus Lagrangian. And as I said, This should be exactly the same. But one of the advantages you can look at here is this is the total moment, but these moments are made up of a number of individual moments. You see a moment due to hip acceleration, thigh velocity, and gravity. So we did use this, and it wasn't. It was in a presentation, so it was not in a publication. But what we looked at was people recovering from an anterior cruciate ligament reconstruction. And one of the things that we found is that the joint moments, and I'm going to go back just a little bit, the joint moments all looked like this between a healthy person and a person who had recovered from ACL surgery after 6 months. That was fine. And so the obvious conclusion there would be, oh, you're ready to go back to, you're ready to go back to, I'm going the wrong way. You're ready to go back to action. But when we use these equations here and looked at all of these individual moments, what we found out was that these can be added up in many different ways to give you this. And so there was a huge difference between all of these moments between the person who had the ACL reconstruction and the healthy person. But there was no difference here. So that's why this was useful to us. And what you can see here, there are actually two lines here. This is the ankle moment. You can see that the overlaid Newton-Euler and Lagrange, they were exactly the same. And also in the knee, they were exactly the same. Well, with the exception here during swing. In the hip, they were a little bit different, but not much, not much. So you can use either method to calculate. In 2D, they're pretty routine. Now, these are caution notes. And I wanted to show you this because this will become important in a few minutes. It's commonly misinterpreted that the resultant reaction forces are bone contact forces. And the moments at the joints are due to muscle forces. This is not true. They're just not true. One of the things that you hear, and you hear this at many conferences, they talk about loading of a joint. And what they use for loading of a joint is the moment at the joint. They say this is joint loading. Well, it's only a part of joint loading. It's not completely joint loading. And so that's basically an error. Okay, the next thing with joint moments, a change in angle cannot be attributed to any one moment or any single muscle. Now, if you noted, I talked about quadriceps muscles. We can say that the joint moment is maybe related to, the quadriceps muscle, but there are 4 quadriceps muscles. I can't tell you which one is which. Okay. I said this just a few minutes ago, but joint moments do not represent the load on the joint. And we'll find that out when we try to go to look at individual muscles. Joint load is the total of muscle forces, ligament forces, contact forces, and inertial forces. And that's why you can't say that the moment is a loading moment. It's not. It's part of a loading moment, but not a loading moment. You know, if I were to truly look at this and try to calculate the moment at the ankle, you notice how many different things that I would have to add in to contribute to that. And of course, the reaction forces of all of this and the moment caused by all of this is not necessarily related simply to loading. Now, I wanted to do this very, very quickly, but energy, work, and power. Energy is the ability to do work. Work can be defined as the change in energy. Okay. And then mechanical work is the work done when the total mechanical energy of the system changes. So work, the change in energy, and this usually refers to energy at one point in time to energy at another point in time. And this has been used quite a bit by the researchers who used to be, are all retired now, David Winter, Bob Norman. And we have average power, which is the change in energy as a function of time. So it's the derivative. Okay. Now, these have been used to talk about muscle power, and muscle power, and again, this is not an individual muscle. This is basically a group of muscles. So positive work is when the angular velocity and the moment are in the same direction. Okay. And here, when they're in the same direction, well, this would be like a flexor action. This would be more of an extensor action. And then negative work, this would be when you have eccentric actions. Okay. This is less popular in the literature now in using this type of analysis, because this gives you, the average of a muscle group rather than individual muscles. And what we're striving for is individual muscles. So I've used an example here of just ankle. And you can see here, this is a dorsiflexion, plantar flexion. This is all during the support phase. And you notice here, remember I said in the moment, this is in walking, the moment here is a dorsiflexor moment, okay, but here is a plantar flexor moment. And when you look at the area under this curve, basically, it gives you this large plantar flexor power. Okay, this large plantar flexor power, which Winter used to say that this is basically the strongest action you have at any particular joint, and also because of the leverage of the joint too. So, like I said, I don't use this anymore, nor do I know anyone who really does. You can also calculate joint power, which is the joint reaction force times the velocity. Okay, so the key thing in everything that we're trying to do is we're trying to get to individual muscles. And we can't do that, as you can see through just the joint moments. But the joint moments can lead us to a part way. And so what I started using was a technique called static optimization. Okay, and this would give us an interpretation of the resultant joint kinetics, and it would calculate the individual structural forces. So you've seen this before. This is just the inverse dynamics approach. But now we're going to apply some external forces, and this is now the muscle and individual muscle and ligamentous forces. And we're going to calculate the joint reaction forces. And what this is going to give us is muscle forces, bone forces, and ligament forces. Okay, this is the whole procedure here called static optimization. And it's a lot easier than you would think. But what you have to do in setting it up, you have to make a lot of assumptions. So I'm going to start off and show you how you get rid of a lot of these assumptions. Now, remember, in 3D, Even if we have 3D joint moments, we have 6 equations. And if you remember from math that if you have 6 equations, you can only solve for 6 unknowns. Okay. So if you look at this is the human knee, or at least a cartoon of the human knee. In the human knee joint, you have 10 muscle forces, 4 ligament forces, 2 bone contact forces, and these are all vectors. So the resultant force would be the sum of all of the muscles, the sum of the bone forces, bone contact forces, and the sum of the ligament forces. Now you can see what that does already. Gives us 16 unknowns. Okay, and of course, in terms of the moments, you have all of the same problems. This is the force due to the muscles, and these are the moment arms here, and the moment arms of the bones, and and so what this gives us is 48 unknowns. And remember, we only have 6 equations. So how do we get rid of the other 42 unknowns? And it's logical. We have more unknowns than equations, so we can't do it. So we've got lots of extra muscles and things. And this has been very, very widely studied in terms of Bernstein's degrees of freedom problem. And Greg Caldwell wrote a paper on the general distribution problem. How do you distribute all of these forces in the force sharing problem? So the easiest way to do this is we simplify the problem. So we make a couple of assumptions. We say that the muscle forces and the bone contact forces are much, much greater than the ligament forces. So we throw out the ligament forces. So the resultant force is just the sum of the muscle forces and the sum of the bone contact forces. And we do the same thing here. We say that the we can say the distance to the muscle forces, is much greater than that to the bone forces. So we won't calculate the moments about the bone forces. And what we can do is establish values for R. This is the moment arm. And we can get this from cadaver studies or musculoskeletal models. You can also just look up in many papers will give you the moment arms for the muscles of interest. And so what are you left with now? We've got 30 unknown muscle force vectors. We can estimate their lines of action, and we've got that down to 10 unknowns. That is muscle force magnitudes. And how do we get this down even further? We assume periods of inactivity, and we can lump muscles together. For instance, we can look at all the vasti muscles instead of looking at them individually. And this is basically a reduction approach. So you can see we can take a huge problem and start making assumptions and narrowing it down. Of course, what if you don't want to do this? What if you want or can't make any of these assumptions? What if we want to know all of the forces all of the times? That becomes a problem. And what we can do then is physiologically look at active and passive structural forces. And you can see we're now back to what we started with. Muscles, bones, and ligaments. And we can lump all of these into inertial forces, gravity forces, and external forces, and their effects. Okay, so the mathematical technique that we use is called the minimization, or it can be also a maximization technique. And all of this is leading up to basically how to do this in MATLAB. And the terminology we should use here is J is called the optimality criteria. X we'll call a design variable, and X star will be an optimal solution. So we have equality constraints, inequality constraints, and then a side constraint, okay? These two are very obvious. The side constraint, LB and UB, what we do is we put an upper bound and a lower bound on the actual force that the muscle can exert. I mean, we can't put a lower bound of 0 because we know that the muscle will exert some force. And we can't put an upper bound of infinity because that would give us solutions that were just unrealistic. So what we're trying to do is just to constrain everything to make the values that we get out more realistic. In other words, we're restricting the solution domain. Okay, so here we're going to minimize J. And J is the objective function. Okay, and is subject to these constraints. Okay. And there are ways of doing this. We're going to use an analytical approach, and we're going to do it in MATLAB. So what we're going to do is basically say minimize some function of the muscular forces. Okay, and we're going to include some things nonlinear, and we should have some physiological underpinnings. This is the boundaries that we're setting. And the way we normally do this is we minimize the sum of the cubed muscle stresses. Okay. In other words, the muscle moments, we minimize the sum of the muscle moments. Okay, and distribute them across all of the muscles of interest. So this is a 2D free body diagram. So step by step, we perform an inverse dynamics analysis, which we've gone over. We acquire the muscle moment arms, and we can do this from the literature or from some program or some polynomial fitting program. Get these values, probably from the literature is the easiest. And then what we do is we acquire the peak muscle forces. This is basically from estimates of muscle size rather, and from modeling. Okay. Now all of this can be done in MATLAB, and nicely in MATLAB, there's a function to do this. It's called if min con. And this is a static optimization minimization program. And this is the only line you need to do this in MATLAB. Of course, this will only do one muscle at one instant in time. So if you have 11 muscles, you do this 11 times once for each muscle. And of course, that only gives you one instant in time. So then you would do it X number of times. So when you do this in programming in MATLAB, the actual minimization is very simple. And I will show you what all of these things mean. What is the problem is that all of the other stuff that you have to get in the right format to put into this equation. So X star, okay, that right here is your muscle forces that you're going to get out. Okay. And J here, basically is your cost function. This is a scalar. So this is the M file or the MATLAB file defining your objective function. And so what you normally do is to start off and put a guess. Okay, some guess for the initial guess. And this is usually what you do is, you can either put this just below the lower bound that you stipulated before. These two parameters are not used. AEQ represents the muscle moment arms, and this is a matrix. Okay. B is the joint moments. That's your the vector for the joint moments. These are the upper and lower bounds on the forces. And these are your nonlinear constraints, and we don't normally use these, or at least I don't. And then this thing called options, set algorithmic options. You know, usually you put in here for optimum set, and that's a default that's used in MATLAB. So, like I said, you know, this is really all you need to get the individual muscle forces. So what you can do then, this procedure is for one time step. As I said, you loop for this for 100 times if you want over a support phase for one muscle. Okay, so if you had 11 muscles, you'd do this 11 times over 100 time steps. This actually here, I took from OpenSim, but I did the static optimization in OpenSim. These are all the muscles that we used. You know, actually, you can see, I can't remember, I think there's about 40 muscles in this. And you can't do that with 40 muscles. It's quicker if you do it with fewer muscles. This is a key thing here. Check your output. Is it reasonable? And the magnitude should be realistic. If you're getting magnitudes of muscle forces of, you know, hundreds of thousands of newtons, you know, there's something wrong there. Okay. And the histories should be smooth. If the moments are smooth, the histories of the muscles should be relatively smooth. And what you can do then, once you have the muscle forces, you can start and calculate muscle orientations and muscle contact forces. What we've done recently with the static optimization that we did in OpenSim, we've started to calculate muscle forces because we were interested in a cutting maneuver, you know, with a person who was running and then had to cut to one side. And we're looking at the contact forces of the tibia, of the heads of the contact forces on the medial and lateral tibia. Okay, so this is a paper that was done by Elizabeth Russell, and this used static optimization. And what she was interested in here was lateral wedges. This is an orthotic. And the lateral wedges were put in the lateral part of the shoe to wedge the orientation of the calcaneus. And we were looking at the load. And we had two groups, a control group and an overweight group. The control group had a BMI of about, I think it was about 25 or less, and the obese were over 35. And if we look at the free moment, the frontal moment of the knee, so this is the ABA deduction moment, and you can see the obese had significantly larger free moment or knee moment than the control group, but the lateral wedge really didn't do much for either group. And if we looked at the contact forces, the same thing can be said. What we were looking at, this was not the individual medial and lateral contact forces. This was the contact force, is basically the sum of the two forces. And again, you can see that the lateral wedge did not alleviate the contact forces in the knee, the axial contact forces. Okay, so this is how you can use this. This is another study that, again, when Elizabeth and Allison and Ross Miller were all PhD students, and Chris O'Connor was a PhD student who had just graduated. And we were interested in the extrinsic foot muscles during running. And what we did was we had varus, valgus, and neutral shoes. So these shoes, the varus and valgus, put the feet into either an extreme pronated position or extreme supinated position. And then you had the neutral shoe. Now, the extrinsic foot muscles are really the muscles that accommodate foot motion, but originate in the calf, in the leg. And so this is a cross section that we did on MRI. This is the tibia and the fibula. You can see here, this is the gastroc, the two heads of the gastroc, and the soleus muscle. And this is the flexor hallucis longus, and so on, the tibialis posterior and the tibialis anterior. Okay. So we looked at these and we did a static optimization of these individuals running. And we looked at the muscles, the extensor digitorum longus, the soleus, tibialis anterior, the gastroc, the peroneus longus, and the tibialis posterior. So in doing this, you can see that the extensor digitorum longus was the most affected by these treatments. The soleus was not. Tibialis anterior was later in stance, but not as much in early stance. The gastroc was not affected. Okay. The peroneus longus, you can see, was if I remember correctly, this was the foot in the extreme supinated position, and a little bit in the tibialis posterior. But this is how you would use. You formulate a question that included the muscle forces, and if you're interested in the individual muscle forces, then you can do a static optimization. This one was done by a former student, Ross Miller, but this was after he had left Massachusetts. And I wanted to do this because this was an intriguing study. And the question was, why don't most runners get knee osteoarthritis? Remember, knee osteoarthritis is thought to be a constant loading of the knee. And if you run, obviously you run a lot of steps, and why don't runners get knee osteoarthritis? And strangely enough, they don't. And basically, what Ross said is, this a case for a per unit distance load? So if we just look at the peak load without correcting it for the distance run, you can see there's a huge difference between walking and running. And this is significant. But if you take this load and scale it to the distance run or the distance walked, you notice there's no difference. And hence, they suggested that running in individuals with healthy knees does not induce joint loads that are greater than walking. And like I said, if we just looked at the peak loads, you'd say, oh, God, you should never run. Okay. So it was an interesting study, and all done with static optimization, by the way. So I've talked a lot. And so during running, the primary external force is the ground reaction force. Okay. And the vertical component is composed of passive and active peaks. The passive mainly a result of the joint geometry, and the active peaks mainly a result of muscle action. Okay. And the passive peak comprised by the lower extremity contact with the ground, and the passive peak is attenuated mostly by passive tissues. The active peak is a result of the mass, the rest of the mass of the body except for the contact limb. And it is the active peak, maybe attenuated is the wrong word here, activated by the result of muscles pushing off against the ground. And we can calculate joint moments using a Newton-Euler or a Lagrangian approach. And the two misconceptions, the joint reaction forces are bone contact forces, and the moment at the joints is not as due to muscle forces. And both of these are not true. Okay. The moment at the joint is not a loading moment. It's part of a loading moment. We can use another method called static optimization to get individual muscle forces, and also to further get joint contact and even ligament forces. And so I thought I would show you a little bit of Massachusetts. This is obviously during wintertime. And I was telling Juliana before, when she first came, I think she was here in Massachusetts for 2 days, and we got a snowstorm much greater than this. This is the University Chapel. This is the library. And this is the Connecticut River Valley in which the university is. You can see the university right there. This is our grad research tower. This is the campus hotel. And if you look right there where my pointer is, that's the building where the biomechanics lab is. Okay. Anyway, if you have any questions, I'd be happy to try and answer them. Okay. So I'll return the screen. Or actually, what I'll do is I'll just minimize this. So if you have any questions, I can answer them. I don't know how to get back to the.
To get back to the gallery.
Yeah, how do we get back to the pictures?
Oh, for your presentation?
Yeah. No, it's all right. Look, I don't need that. I can see you on the side here.
Yes.
Okay.
Yeah. Well, if you want to, because if you want to see all of us, you can stop sharing, and if you need it.
Yeah, I know. I don't know how to stop sharing though.
If you go to the bottom.
Yeah.
Then probably you'll see.
Oh.
No. You go to the bottom. Not of this, not of the Zoom window, but the bottom of your computer. Yes, this one, the right one.
Look, let's just leave it. I don't want to waste your time.
Okay, Joe, there are 2 questions already. Vinicius, he's asking if what is the influence of arm movements in the passive peak, the first one.
Yeah. We've done several studies in terms of the arm movements. In fact, Ross Miller did one where he constrained the arm movements. And the arm movements really don't contribute a lot to the passive peak, but they do contribute to the active peak. Okay, the passive peak is really a function of the lower extremity, the leg that contacts the ground, that lower extremity. Okay, the movement of the arms, it's really an angular momentum problem about the axial, about the vertical axis. Okay.
Okay.
It doesn't, like I said, it does not affect, at least from our research, it does not affect the passive peak, but it does. It will affect the active peak.
And the other question he's asking because he's asking about how reliable is to use accelerometers to have the moments, the joint moments.
Well, there are people now using multiple accelerometers. In fact, I just read a paper today, this morning, and what they have used IMUs, and the IMUs basically have an accelerometer in them. And what they're doing is they have a technique to generate the ground reaction forces. And what happens with that is that it tends to attenuate the passive peak. It gets the active peak pretty well, but it tends to attenuate the passive peak. But I've not done it. But there are people who have done used accelerometers to get not just one accelerometer, but a series of accelerometers to get the passive peak.
Yes, indeed. Well,
Thank you, Professor.
the other question, well, Alessandra, she's also asking, but she's asking how reliable is using these IMUs to have ground reaction forces information. It's just like you said.
You know, like it depends. As I said, there are people who have done this. You know, there are people who have used accelerometers, not one accelerometer, but multiple accelerometers. And what the paper that I read this morning used multiple accelerometers, and then they used I can't remember what technique they used, but it was the neural network technique in order to predict the ground reaction force. And as I said, what they were getting was they were getting the ground. It looked like the ground reaction force, but if they also collected at the same time, they collected real ground reaction forces on a forced treadmill, and so they're able to compare the two. And what it did was it reduced the passive impact or the passive peak, but it didn't affect the active peak. But like I said, I've not done this, and I'm just relating someone else's, study.
Yeah.
I can tell you one of the things that they're going to present the study at the International Society of Biomechanics meeting, which is going to be a virtual meeting from Stockholm, Sweden. So if you're interested, you'll hear it there.
Cool. Yeah, and Joe, maybe part of this problem is that, as you said at the beginning, if you look at across the body, dumping the impact that you had on your foot across the body, yes, and then probably this passive voice is disappearing across as far you get from the foot.
Yeah. But don't forget though, the ground reaction forces act as if they're all acting at the center of mass.
Yeah.
Okay. Just keep that in mind when you're, and I think a lot of people forget that.
Yeah.
That acceleration, the sum of the forces equal mass times acceleration. That acceleration is the acceleration about the center of masses of all of the segments. But then when you put them all together, that's the center of mass of the body.
Yes. Joe, the other question, Lydia, she's asking is it possible to predict injuries, thinking about the stress forces, thinking about the stress injuries.
Yeah. One of the things that I worked on quite recently with Hannah Rice from England, from the University of Exeter, England. She and I, when she was here at UMass, we put together a program that calculated tibial stresses during running. And one of the things that we were looking at is, can we predict tibial stress fractures? We could calculate the stresses on the tibia during running, but the missing link is we don't know how much of those stresses will cause a stress fracture. And that's the thing is, we don't know. We don't know what the stresses are that will cause a fracture or cause a stress fracture. But we can infer that in certain people, if the tibial stresses are very, very high, we can suggest that that's a possibility that, or I shouldn't say very higher than normal. You know, that person might be prone to a stress fracture.
Okay, Alessandra, why don't you open your microphone and ask by yourself your question? Oh, she can talk now.
No.
Alessandra, she's asking Joe if if you do think that we are moving to a new era, new times, thinking about the IMUs.
Yeah, I do. The thing, everything I've talked about today was laboratory-based research. And of course, laboratory-based research is not ecological. You know, you've got a static environment. And, you know, in predicting if we're doing anything in human movement, and you know, you want to be in the environment in which the activity takes place. And IMUs, you know, in conjunction with, you know, if they're Bluetooth, you can get it directly into your computer, or if you have a data log or anything like that, you can send a person out to run and get the data actually in terms of the, you know, in the environment in which the person would normally operate. And so I think IMU studies are ultimately going to be proven to be more ecological. The trick is now, can we relate, you know, the IMUs to the actual measurements that we're trying to make?
Just like the markerless systems.
Yeah, the markerless systems, you know, I was just talking to Scott Selby, who has a now markerless system. I think it's called Thea. And he was showing me the results of the markerless system. And, you know, the 3D angles are remarkable, you know. And I did a little study with a friend of mine in Singapore, and we just had someone walking on a treadmill, and we did a very, very crude markerless tracking program. And we were getting, you know, comparable values to what we got in, you know, digitizing the data. We're getting comparable values, you know, differences maybe 1 or 2 degrees, you know.
Yeah.
Now, of course, in a 6 degree of freedom in the secondary planes, that might be too much. But
yes,
you know, it's interesting. One of my postdocs just took a position in the biomechanics lab with the New York Yankees baseball team, and they have markerless tracking. And during games for the rest of this season, every pitcher from the New York Yankees will be markerless tracking will be focused on them during their pitches, so that they'll have every pitch that every pitcher pitches during the season, and they will be able to track it in 3D.
Oh, cool. Sarah, don't you want to open your microphone to make your question?
Yes, sure. Thank you very much for the presentation. It's very important to me. Many things I'm learning today blow my mind. And Professor, I was thinking about if it's possible the activate peak in treadmill on microgravity or lower gravity running.
Mm-hmm. Well,
ablation of activated peak. I don't know.
Yeah, there have been studies done on that. I have not done them, but I think what happens in the low gravity situations, they use that gravity thing, and put them on a treadmill.
Yes, to push
I think,
you down, right?
yeah, I think the active peak actually decreases
Right. So
during running.
it's not, yes. So, but it's not too much important for a biomechanical future analysis in our walk space in another planet, for example.
Well, again, we talk about walking and running, but there are more modes of locomotion than walking and running.
I understand.
That you see little kids doing it, the galloping, where they keep one foot out in front all the time, and
Yes.
it's sort of a run, and also skipping. And what was interesting, if you remember, well, you probably don't remember, you're too young, but if you saw the astronauts locomote on the moon, they did not
Yes.
use a normal walking stride. They used a galloping stride, with
Yes.
one foot constantly out in front of the other. And, I think that's a function of two things, the low gravity, okay, and the spacesuit that they're wearing. But the trick is that, we have to think that when you're in microgravity, it will induce, the way you run or walk.
Okay, I understand. I'm sorry for the full question, because I am studying the microgravity and muscles, and that's the first time I was thinking about biomechanical analysis and microgravity, and I'm very curious about it. Thank you very much.
Yeah. Are you using EMG?
I'm sorry, I don't understand.
In the microgravity studies, are you using EMG, electromyography?
No, actually, for planned futures, yes, I'm planning do this for I am doing epidemiology description for astronauts with Professor Moshi, but in future plans, I was wondering use the EMG.
Yeah, if you're using the same mic to induce microgravity that I've seen, you can't really use cameras, but that's where the IMUs would be useful.
Yes. Yes, will be.
Yeah.
Thank you very much.
Okay.
Franklin,
Bye-bye.
Open your microphone and make the question.
Hi, Professor Hamill. Can you hear me?
How are you doing? Uh-huh.
Nice to see you again. It's a pleasure for me. So why do the Newton-Euler and Lagrange approach show different results for the hip, special for the hip?
I think it's not a function of the two methods. The two methods should give exactly the same results.
Yes.
Basically, the further away you get, is you get slight fluctuations in the position data, and don't forget you have to estimate the joint centers, and it may be a little bit harder to it's easy to estimate the ankle joint center and the knee joint center. It's harder with the hip.
Could we consider that it's about the propagation of uncertainty?
It's it's a propagation of error.
Okay.
Yeah. But the thing is, if we had absolutely perfect data with no error, the results of the Lagrangian and Newton-Euler would be exactly the same.
Yes. Thank you, Professor.
Okay.
Thiago.
Actually, can I just add something?
Yes, sure.
The reason why you would choose one method over another method, okay, is all based on the question you're asking. One method is, peculiarly for energy. and that would be the Lagrangian. But like I said, if you want to go on to look at individual muscles, it doesn't matter. A moment is a moment, and they should, you can use them very easily.
Sure. Thank you.
Thiago.
Oh, thank you. Thank you for your presentation, Joe. And I have two questions about carbon fiber plate. What do you think about these running shoes that promise greater energy restitution due to a carbon fiber plate in midsole? And do you think that moment of force and muscle force can change because of carbon fiber plates?
I certainly do. I think putting carbon fiber plate in the shoes is basically cheating. I think it's cheating. It's essentially the same argument that people used. Remember when Oscar Pistorius, with his, what did they call that particular leg?
Yes.
Anyway, it's the same thing. It's putting energy into the system that's not there normally. And I know that the Olympic Committee has basically said that if the shoes with carbon fiber plates are not available to everybody, they can't be used. And well, now all of the top runners in the world are going to have those shoes, but ultimately I think it's cheating.
Okay.
Even if everyone is doing it, I think it's cheating.
That's true.
But I think your question is a good one in the sense that how will that affect the moments at the joints? And if it affects the moments of the joints, ultimately it will affect the muscles. So I can give you an opinion, but I can't give you an answer.
I don't know, because it's a polemic topic now in running races, and I don't know, but I've read article, opinion article of Ben Omig, and he talks about teeter totter effect. To explain the restitution, run restitution force. And I have curiosity to know about the moment force and the muscle force, about that.
Yeah, what was one of the things that one of my honors students did a number of years ago, when this whole thing first came out about the plates, we had shoes made up with plates in them, and so we had women running these shoes, and we measured the oxygen consumption, and we had men running the same shoes. And one of the things we found is, interesting enough, the shoes benefited the men, but didn't benefit the women at all. And as it turns out, it means that it was a function of body mass. The men, all of the men were basically about the same mass, and the women, were substantially lighter. And what that indicates is that, I wear a size 9 shoe, a 43 millimeter shoe, 43 centimeter shoe. And I know my body mass is about 75 kilos. But if there's this person with the same size shoe as me, but was lighter, they wouldn't get the benefit of the insert in the shoe. And so basically what this would have to be is every person that wears those shoes would have to be fitted and tested for the exact optimal result. And what this means is that you know, you would have to have someone optimizing the shoes. And I know for a fact that the Nike shoes, the Vapor, is that what they're called? The Vapor that have that insert in the shoes. It's the same insert for everybody. So that means some people will get a benefit and most people won't. So.
Okay. Okay, thank you.
Mario, make your question.
Hi, Professor Hamill. It's a very pleasure to speak with you. Thank you very much for our presentation. I have a question for you. In your point of view, could we use the calculation of internal forces for evaluation athlete performance?
Mm-hmm. Oh yeah, I mean, I know, you know, I know people are doing it. You know, using optimization methods to calculate the individual muscles of you know, elite athletes. But the process is the same that I went through today. You know, is you calculate joint moments, you input those into the optimization program, and you get the muscles. Now it depends basically on you know, how many muscles you want. I'm trying to think the study that we did on the tibial stresses. I think we used a total of 22 muscles in the lower extremity. I mean, you can't just use the muscles across one joint because some of them are multi-joint muscles in that. So, you know, you can get any number of muscles that you want, but you need the 3D joint moments ultimately to start with.
In your point of view, is it better than traditional form to evaluation the force in the athletes, for example?
It's more detailed. You see, if you don't try to account for the individual muscles, all you can account for is basically muscle groups. You know, and that might be not enough detail for you.
Mm-hmm.
Okay, thank you very much.
Okay.
Vinicius.
Okay. Professor, first of all, thank you for the great presentation. It's a great honor being here to speak with you. Do you believe that people who have reduced arm swing during usual locomotion have a greater energy consumption?
That's a difficult question. You know, people have, my colleague you know, Richard Van Emmerich, Luis.
Mm-hmm. Yes.
Richard has a number of papers on, not necessarily on oxygen consumption, but on arm swing. And arm swing is significantly related to leg swing, and also the trunk rotation. But you know, the arm swing, the excursion or the range of motion of the arm swing will change as a function of you know, leg swing, and which means that really you increase your step length, you increase leg swing, you will increase arm swing to counteract that. As I said before, it's an angular momentum problem. But I can't think of any, you know, or at least off the top of my head, I can't think of anyone who's related that to oxygen consumption. But if you think about it, that if you run faster, leg length will increase, which means your oxygen consumption will increase, which means your arm swing will increase. So I don't know of anyone who's done that, but you know, it makes sense that arm swing will affect, or the range of motion and the frequency of arm swing will affect oxygen consumption to some amount.
Thank you, Professor. Matter of fact, you said that arm swing are strictly related to the leg movement.
Well, no, I didn't say it's strictly related. It is very closely related, because remember that when you swing your legs, one goes forward, one goes backward, you're inducing a rotation in the total body. And so that you don't keep running in a circle, that rotation has to be counteracted, and it's counteracted by the the pelvis and the thorax and the arms have to counteract the the leg swing. That's why, if you notice, the arms rotate in one direction, the legs go in the opposite direction. But what they do is everything cancels out. And that's strictly an angular momentum problem. There was a really good paper by Rick Heinrichs, and it's a very old paper, very old to you, not to me. It was, I think, published in about 1985 or 86 on this, the effect of arm swing.
Okay, thank you very much, Professor.
Okay.
May I ask a question?
Sure, Thiago, go on.
Thank you. Professor Hamill, thank you for your talk. And it's more of a curiosity I have, but is this method that you presented today, or has it been used in youth athletes to either guide particular movements, say jump or a running, or to identify lesion-prone athletes and then provide a way of correcting those things or boosting those things early on?
Which method are you talking about?
To calculate or to simulate the ground, the forces and how they propagate through the body.
Oh, yeah, yes, it has been.
Yeah.
It's hard to do at the individual joint level, but it can be done. Most of the problem is that other than the distal tibia and the head, you have to find a spot where there's not very much skin and fat tissue over the bone, where you can mount accelerometers. I mean, we've played around with it. You don't get a nice smooth, attenuation of the shock as it goes through the body. But yeah, we have, you can do it. We were just interested in the body as a whole and looking at this impact force up to the head.
I see. Yeah. What I was wondering is, it's really, the individual joints that, for instance, if you are trying to do a high jump, but you are perhaps having a very strange, let's say, rotation or lowering of your center of mass before you jump, you might be overloading some hip joints, or later on your back or your knee, and which might not be a problem early on, but as you go on training and playing, say 10 years later or so, this might be a huge problem, or even earlier. So that might be interesting to,
Yeah, I know there's lots of studies of high jumpers jumping off a force platform, and so that's pretty well known in the literature. But if you combined the force platform data with the markerless tracking data to get the joint and calculate joint moments, and then using that to put into an optimization model to look at individual muscle forces, that would give you an indication of if you got muscle forces in certain muscles of an injured person versus non-injured person, that would be interesting. But I don't know if anyone has done anything like that yet. The people that have been driving, the markerless tracking have been sports teams who have lots of money.
Okay, thank you for your insights. Yeah.
Joe,
Yeah.
do you have an opinion why people prefer thinking about forces, not thinking about energy? Because it's easier. I don't know if because it's easier to use Newton-Euler equations than Lagrange equations, or it is because the definition of energy is also in physics is also very nebulous.
Yeah. The whole problem is that when you use an energy approach, you always seem to run into the problem of violating some of the laws of thermodynamics.
Mm-hmm.
You end up with more energy than out than you put in. You know, I just think it's, you know, a Newton-Euler approach was the approach that most people used originally when we were doing, you know, joint moments. And I think the Lagrangian, you know, not as many people are familiar with Lagrangian mechanics. I know, you know, when I was a graduate student, you know, we would spend months on Newton-Euler approach, and then about 2 lectures on the Lagrangian approach.
Yes, you're right. Yeah. Yeah, even if at physics, we don't spend a lot of time studying using Lagrange.
Yeah.
But then I was thinking about the other approach, like for example, Zasiorsky enjoy about discussing, for example, the pseudo forces, the Coriolis and centripetal and the other ones. What do you think about this approach to understand internal forces?
Well, I mean, all of those, theoretically, all of those approaches should give you exactly the same results.
Yes.
The other method that is starting to be used quite a bit now is Keynes' method. Keynes' method is very, very, very similar to Lagrange in that, you know, it's a combination, and Keynes' method, you know, gives you the same type of information that Lagrange does. It's set up in a similar way, and Gary Yamaguchi, who used to be at Arizona State in engineering, he wrote a book on Keynes' method, and I don't know very many people that actually use it. But what's interesting, if you use OpenSim and you do a lot of the analysis in OpenSim, Keynes' method is used in that, although people don't realize that that's what's being used.
But don't you think that if we start to use a lot OpenSim and using the inertial units, and for example, let's add artificial intelligence, then are we going to turn that into a black box to most of the people?
It already is a black box. You know, when I was a student, you know, I graduated with my PhD 40 years ago. If you didn't know how to program, there were no, that you couldn't collect data, you know, because the programs didn't exist, you know, and then we started getting you know, programs like C-Motion, which you don't really have to know how to do anything except get the data in there to get and get data out. And of course, OpenSim is very similar. Now, anybody can do a static optimization, you know, much easier than what I presented today. You can do it. And what you can also do a simulation without knowing how to actually do it. You know, I remember at a conference, someone was doing a presentation, and I could tell that they really didn't know what they were talking about. And I was feeling very mischievous this particular day. And so I asked him to explain a very technical point, and he couldn't do it. But he had done the simulation.
Yes.
It is, everything is becoming a black box. I mean, I don't know if you remember, Luis, but again, when I was a student, when we digitized, we have to use the pointer.
Yeah.
And show one frame at a time and do the pointer. And now, you can digitize a 3D running motion in 15 seconds.
Here in Brazil, people were used to associate this method of digitizing markers as Marlene Adrian method, because at that time there was only one or two books in biomechanics, and one of the books was of the Marlene Adrian's book, and she was suggesting to do that. So I remember that in Brazil, this method was used to call as Marlene Adrian's method.
Yeah. Well, I mean, I did that for a number of years. I remember for my dissertation, and again, this was done in 1979. I hand digitized like that over 12,000 frames of data.
Do you still have the films?
Do I?
Or no? Yeah.
No, I left them at Oregon when I left. But I keep saying that biomechanists of my age who did all of that digitizing have to wear glasses now.
Yes.
Because we're blind.
Yeah. Yes. I agree. So, my students, do you have any other question? Well, Joe, was a great honor to have you here. You always give a very clear message, and I think that was very important to the students to hear all this information about biomechanics. Unfortunately, we are very far away from, but we expect that this pandemic will end and be able to come again. Anyway, are you going to be at IFAB?
No, I can't. No, I thought IFAB was going to be virtual.
It's going to be virtual.
Yeah.
It's going to be virtual.
No, I've sort of gotten away from that whole group.
Okay.
My research is more into motor control now, and what I'm doing now is, or what I'm most interested in now is the relationship of vision and motion.
Well, vision and motion. That's something nice. That's also nice. Yes, you're doing motor control knowing that exists physics.
Yeah, that's true. Yeah.
Yes.
Yeah.
Yeah. Well, Joe, I was just Ulysses. He had to leave earlier, but I was just talking to Ulysses about one idea I had that we're gonna discuss a little bit about coordination and the other things as well.
Okay. Anytime you want to talk, just Zoom is nice for that.
Yes,
at least,
indeed.
I hate talking on the phone, but Zoom, at least I can see people.
Yes, you're right. So, I think that for today we are okay.
Okay.
Joe, and if it was possible, then if you have updated your file.
Yeah, I did. I will send it to you.
And then I send to the students.
Yeah.
And,
okay.
And thank you so much. And I also, Joe, I had another question. What do you think about measuring the mechanical properties of fascia. And
all I can say is,
including that into biomechanical, into the regular biomechanical analysis.
well, I mean, what you can do is do the same thing that I talked about today, except, in terms of, you have, looking at the optimization of muscle, bone, ligament. You can look at cartilage, and of course you can include something for fascia. And
Yes.
and I think OpenSim will allow you to do that.
Mm-hmm.
Yeah, I mean that's a thing that people have ignored because they say that the forces, the fascia doesn't exert a large enough force to really affect, but no one really knows how much force it does. I know there's a group at where are they? They're actually very close to here in Connecticut that they're looking at fascia. I can't remember their exact names, who it is, but I know that they've looked at it because I've heard them talk about it. And they're using an optimization type analysis.
Mm-hmm.
Yeah. Anyway, it's beyond my capabilities. So, if I don't understand it, I don't do it.
Okay. Yes. I agree. I agree. Well, thank you, Joe, so much for your time.
Thank you.
And let's do
Thank
something
you so much.
something that I forgot to do yesterday. So, guys, please open your cameras. So then Joe will be able to see all of you.
Anyway, thank you very much for listening. I appreciate it.
Yes, that's nice. That's nice. Okay, so Joe.
Thanks so much, Joe.
So if anyone wants to say goodbye to Joe, it's time to. Thank you so much.
Bye.
Bye, Joe. Stay safe,
Professor.
Joe.
It was a great honor hear from you today. Thank you.
Thank you.
Bye, Joe.
Thanks, Moshi. Thank you, Joe. See you.
Bye, Juliana.
Bye.
Okay, Luis.
Thank you
Bye,
very
bye,
much.
Joe. Thank you,
Bye-bye.
Joe. Bye-bye. Bye-bye.
Bye.
Bye-bye.
Stay safe. Stay safe,
I will.
Joe.
You too.
Yes, I will. Bye. So I'll end the record.